Good afternoon, everyone. Thank you very much for joining us for this C2 Smarter seminar. Today, it is my pleasure to welcome Dr. Xichen Liu. She is an assistant professor in the Department of Civil and Environmental Engineering at Stony Brook University. And her research focuses on innovating next generation modeling and computational tools for mobility and logistics systems. And she places a special emphasis on connectivity, electrification, and automation. She received her PhD in civil engineering from the University of Michigan, Ann Arbor. So go blue. She also received a master's in operations research and engineering. And while at the University of Michigan, she was actually also a visiting scientist at General Motors. And she was awarded the prestigious Rackham Predoctoral Fellowship in recognition of her dissertation work, and also the Helen Overly Memorial Scholarship by the WTS International Foundation. What is WTS?
It's Women in Transportation.
By Women in Transportation International Foundation. So it's my great pleasure to welcome here Dr. Liu. Please help me welcome her.
Thank you very much for the introduction. So today I'm happy to share my research about inverse learning and intervention of transportation network equilibrium. So before I go to the technical details, I want to briefly reintroduce myself in terms of research. So in one sentence, I'm a transportation system engineer, where I try to develop better tools to model and manage the transportation system. Now, like currently three focus of my research. The first directions is driven by electrifications, where I help policymakers to design better policies to electrify the rideshare companies. And the second directions is driven by automation, where I try to study if we put a autonomous vehicle, like a part of machine intelligence, into the system, how will that impact the behaviors of human drivers? And the second directions, which is the focus of today's discussions, is a connectivity. So the main motivation is now we have more data about how people move every day. And these data have information that is valuable for decision makers to help them better manage the cities and transportation. So we will see how can we designing a equilibrium-based analysis framework to leverage cross-source data to better support strategic decision makings in transportation system. So here's a motivating example. Actually, Google has a project called Greenlight. It leverages the navigation app data, which they're already collecting to understand the congestion patterns of different cities. And then it offers policy recommendations like changing the lightning timings, the signal timings of different cities. Actually, they have a very interesting business model because once you build the pipelines, you can deploy it for many big cities as long as they have the data and does not require additional sensor deployment cost. So there's one current scenarios or limitation that adjusting the green lights may not be able to solve. Think about some very congested regions, like the Manhattan Island. Changing the signal timing alone may have some limited increments when improving the system performance. So in this case, the city planners will always consider more strategic ways. For example, we may want to change the directions of the road network and therefore changing the underlying topologies. Alternatively, planners are considering the demand side policies like congestion pricing to change people's travel patterns. So in order to compare and select among these strategic designs, policymakers need to answer the following questions. That is, we are changing the road network. We are potentially changing people's behavior. How can we anticipate how people react to these policy makings, or what are people's patterns if the road network got changed? So we'll be looking at this kind of strategic transportation planning settings. And actually in the field of transportation, the transportation planners, we have GM theoretical models to capture people's behaviors on a congestion network. So here's an intuitive example. Suppose I want to go from one station to the other. If I'm the only travelers in this road network, then I can just choose the quickest or shortest path. But in reality, many other people want to use the system together with me. So when many people join the road network, congestions happen. So I may benefit by detouring slightly, but actually reducing my travel time. So considering that means my own travel choices or route choices impact by everyone else on this neural network. That will result in a game theoretical settings. We call it a routing games, which consider congested networks, all travelers wants to choose a route that minimize their own travel cost. So using this game theoretical framework, we can predict the steady state of these routing games, or what we call user equilibriums, or verge of equilibrium. If you are familiar with game theories, it is an analogy to the Nash equilibrium, but the players can be infinitely small. So using this steady state as a benchmark, we can go on to compare different strategic plannings in what-if analysis and select the better one. So this is how what we call the network equilibrium modeling paradigms work. In the seminal work of Beckman, McGill, and Weinstein in 1956, they actually show that solving for the equilibrium state of this routing system can be very simple as solving a convex optimization. So in theory, as long as I have a game theoretical models, I can solve for the user equilibriums, and I can use this to support decision making. But in practice, using this pipeline requires us to calibrate the model first, because traveler preferences are not directly observable. That is, these equilibrium models have some parameters, these calibrations, which can be challenging and time-consuming. So what are the new opportunities brought by cross-source data? So even though we still does not directly observe people's travel choice preferences. We don't observe why people choose the pattern, choose the route. But we can indeed observe which route or which path they actually choose through this cross-source data, like the mobile phone data, connected vehicle data, or the social media data. And what's even better, that is, we have a continuous observation of the travel system. We can observe the system for multiple days, and also we can observe, like, for example, on the different weather conditions, the travel pattern will be different. So today we'll be looking at the inverse process. That is, given people's observed behaviors in multi-day data, how can we inversely learning these network equilibrium models by answering the following questions? That is, what is the travel choice preferences can best induce the observed behavior? So we'll be looking at inverse learning problems and see how can this emerging auto differentiation and machine learning tools can help us make this inverse learning process better. So here comes the outline of today's presentation. So first, I want to present inverse learnings, and indeed, I want to show you that it is a very general framework that still offers a systematical way to build existing literatures across in different fields. And after we presenting the inverse learning framework, we're going to look at two different examples of using the inverse learning framework. One uses neural network, and the other uses the semiparametric method. And the third part will compare the different methods, and we will conclude by applying this inverse learning framework to support decision making. So this is a five-part that we will walk through today. So before I go to the technical details, I would like to thank my collaborators, Dr. Yafeng Yin, Shilin, and Zihao Wang from the University of Michigan, which I recently graduated from this summer. And also Dr. Fan Bai and Donald Green from General Models, who offered us the empirical data for us to working with. Okay, so any questions before I go to the first part? Yes.
I just had a question by just saying inverse learning. Are you interested in like the time functions of the link? What are you exactly trying to like?
So maybe I can better answer these questions after actually showing you the inverse learning framework. Okay. Yeah. So before we can define the inverse problem, we need to first properly define the power problem, which is a game theoretical framework. If you are familiar with network equilibrium model, this is known as the Beckman formulations or BMW formulations, which is the classical formulations you will learn from Sheffield's book. So I need to introduce a few mathematical notations here. So let us use H to denote a vector of path flows for all ODs on the neural networks. And we use capital H to denote its visible regions. And we use small v to denote the aggregated link flows, which is also a vector of all the links on the neural network. And this is a matrix that aggregates them together. So these follow problems by changing the path flows and link flows, we will want to minimize what we call is a potential functions. So just for the illustration purpose, we assume it to be convex here. So even though it looks very simple, but these complex programming forward problems can be extended to capture whether people choose to travel or not by considering a elastic demand functions. And also it can be extended to capture more comprehensive route choice behavior beyond choosing the shortest path. So here's the setting. Given this, we want to build a forward problem, but the parameters of these functions. So get back to your questions, it can be the parameters of the link performance functions, or it can be the parameters of the demand functions or route choice preferences, depending on what component you think needs calibration. And these two parameters is not observable. And suppose we do have a yearly average link flow, which is called V bar. So here comes the inverse problem. That is, we want to find a flow, which is denoted by H star, that can satisfy the equilibrium conditions. At the same time, we want to adjust the parameters of these potential functions so that our predicted flows can match our observed flows. To have a more tractable ways to formulate the inverse problems, we want to introduce a functions. It's called the equilibrium gap functions to equivalently represent the equilibrium conditions. So here you can consider if these gap functions equals zeros, then we can approximately consider that our predicted flow is indeed at an equilibrium state. So this is we'll call it IP for inverse learning problems throughout today's presentation. So here's like one fundamental trade-off. Yes.
Sorry, to the sort of data you consider, because you mentioned earlier, so you have the trajectories data.
Yes. That's a good question. So here we're considering a simple setting, starting with one sample. We'll extend it to multiple samples later. Thanks for pointing it out. Okay. So here comes like the first fundamental trade-off when we need to build the inverse learning framework. That is, actually the observed data may deviate from user equilibrium model. Every day when we choose our choices, we may not necessarily at equilibrium state. But at the same time, we want our predictions to satisfy the equilibrium condition because we want to use it as a consistent benchmark to support decision making. As you can see, these 2 points, they're conflicting with each other. So to reconcile this kind of two competing objective functions, there are two ways. The first is as what I presented in the previous slide. That is, if we assume we want to strictly enforce equilibriums, we can enforce the equilibrium conditions as a hard constraint while minimizing the fitting errors as an objective function. Or alternatively, if you believe your data is pretty accurate, you can put your fitting errors as a hard constraint by strictly enforcing the matching with observed functions, while at the same time minimizing the equilibrium gaps as a behavior-based regulatory terms in the objective functions. So this comes up with the first choices we need to make. We want to build the inverse learning framework. That is, we want to select whether we want to prioritize data fittings or whether we want to prioritize equilibrium constraints, which will end up with two different formulations. And the second choices we need to make is there are many different options of what the equilibrium function looks like or what the loss function looks like. And the second thing is we need to select which are the functional form for each different function separately. And finally, the third options or selections we need to make is what are the underlying behaviors or the physics or realities we assume that will happen in the natural equilibrium model. And these assumptions will determine what the functional form looks like in the potential function. So here comes this, so here's an example to illustrate. For example, if I want to choose the equilibrium gap function, one is based on the value functions. That is, we compare our objective functions and the best possible one. That's suppose we select this value function based gap function. And then when we select the potential function, we can start with a general one that we assume it is convex in flow. Or we can make a stronger assumption that we assume it is a multi-convex function. Or an even stronger one, we assume it is linear in flow, which basically considered a congestion-free network. So as you can see, since I varies my options of these equilibrium gap functions and potential functions, we can result in different formulations of inverse learning problems. Also, the second type is based on the Lagrangian dual functions. We can measure the equilibrium gap by looking at the potential functions and its Lagrangian dual lower bound. And this will give to a different formulation. And the other two types are the equilibrium gap functions, if we can reformulate the inverse learning problems as a mathematical program with equilibrium constraints, or as a mathematical program with comparametric constraints. So, and here are the examples in the literature. So far, I hope I have, through these two slides, I hope I have convinced you that the inverse learning framework is actually a very general framework and offers flexibilities in using a systematic ways to interpret and understanding different methods, different literatures across in different fields. This literature, they are known as OD matrix calibrations, that were equilibrium models calibrations, inverse optimizations, or out of distribution generalization, depending on which field this literature comes from. So, given this general or simple inverse learning settings, then we are going to touch upon on the cross of the data. So here's the main differences we have from the data source set. That is, previously we showed that suppose we have a one single yearly average observations. But thanks to the cross of the data, now we can have multi-day observations. So here, for the rest of today's presentation, I will be using the small m to denote that it is a flow associated with one sample or 1 day. And also, another good thing is we can observe some external factors that will change people's behavior and also remains observable on a sample or daily basis. For example, the weather. We expect that on different weathers, the resulting equilibrium, the resulting travel patterns will be different. And given this multi-day observations, we can observe context and noisy link flows on multiple different days. So to leverage these multi-day information, we need to, actually it allows us to learn a context-dependent user equilibrium models by including the context in the objective functions of the forward problems. So look at this formulation. It means that suppose I have different weathers. I change the values of this x and I solve for equilibrium. So for different weathers, I can actually predict different equilibrium state given different input context. So similarly, I need to include the context information when I formulate the inverse problems. And now the context will also appear here in the equilibrium gap function. So as we shown in the previous section, yes.
Sorry, I just had a question. What is the time context that you're talking about here? Is it like this flow, like average hourly flow or like daily flow?
What is
Like
so here one example we can think of is like we are looking at the evening peak hours for every day, and here each m denotes each days or different samples. We have an example to add for that later. Make sense?
Yeah, thank you.
Okay. So as we shown in the previous slide, we do have like different options to design the inverse learning frameworks. And here we want to show two examples that faces a trade-off between goodness of fit of prediction accuracies as well as computational tractability. The first is what we call a non-parametric approach that we want to leverage the power of neural network. So here's the main idea. That is, we don't really know what potential function should look like. It can be a polynomial function, it can be an entropy function, so which one should we choose? So the key message of using this non-parametric approach is instead of predetermining the functional form, we want to approximate the unknown potential functions with a neural networks, and then let the learning process to discover the functional forms directly from the data. And hopefully the functional form we discover will be more flexible than this predetermined functional form. So here's how this non-parametric approach works. Suppose we have a neural network that represents the gradients of the potential function. It has some parameters theta. Then I have the context. Here we are using a special neural network architecture called implicit layers. So you can think of the implicit layers, they are solving a fixed point in the internal so that actually it is enforcing equilibrium conditions within a deep learning pipelines, such that the output of this implicit layer is not any random flow distribution. Actually, it will satisfy the predicted user equilibrium condition. And as mentioned, we have multiple samples, so we can parallelly computing the equilibriums for multiple different samples, and by comparing our predicted flows and our observed flows, we can get a fitting error functions. So this is what we call a forward propagation. Yes?
So you're assuming that your observed flows are in equilibrium.
What's the question again?
So you're observing, you're
Yep.
assuming that your observed flows are in equilibrium.
Not necessarily. So even when we try our best to do our calibrations, these fitting errors may not be zeros.
But I think the network might not be in equilibrium.
Yeah, I agree. So-
What you're forcing, your loss function actually might be forcing the disequilibrium or non-equilibrium.
Yeah, that's a very good question. So I get so here we are not forcing. It's not so through fitting errors, we're not forcing equilibrium conditions here, but rather we are encoding the equilibriums as a hard constraints in the implicit layers, so that there might be different possible fittings, but we are selecting the equilibrium conditions that yields the minimum fitting errors because remember our initial settings, that is we want to support strategic decision makings. We need equilibriums as a prerequisite to help us answer what if questions. That is, if I change the neural network topologies, or if I add or remove one links, I still want to have a consistent benchmark to compare different policies. So that is why we kind of enforcing equilibrium conditions to make sure that our predicted flows have some behavior implications and can be a consistent benchmark for comparison. Does that answer your question?
That's okay.
Yeah, we can discuss later.
Cheers.
Yeah. So actually, this is taking these primal perspectives in our previous inverse learning problem. That is, we are strictly enforcing equilibrium conditions while tries to minimize objective function, minimize fitting errors in the objective function. So this is the forward propagation. The technical challenge is, if you are familiar with network traffic assignment, even though that solving for a single user equilibrium is not that easy. But here we want to solve for multiples, like 32 in parallels. So this do requires us to develop new solution algorithm. And after we calculating the fitting errors, in the back propagations, we want to calculate the gradient with respect to the potential, with respect to the parameters, and then update the parameters to minimize the fitting error. So we call it the back propagation, and the technical challenge we handled is how can we differentiate this from this like implicit layers to make sure that the gradient can be approximated or calculated efficiently. So
So
good,
I
yes.
have one question. So when you introduce at the very beginning that there are two types of methods, two approaches to
Yeah.
kind of like minimizing the fitting error, right? One
Yeah.
is to assume that the observed flow distribution will follow the user equilibrium, and the other is not.
I think now both that two formulations, none of them assume that the observed flow is at equilibrium state.
Okay, then I'm just wondering which approach are you actually adopting in your presentation?
Yeah, I think your problems echoes the previous
Yes,
question.
yes.
Is here we are assuming that we want to strictly enforce equilibrium constraints
Okay.
by including them as a hard constraints while minimizing the fitting errors in the objective function.
Okay.
We can get back to that later in the Q&A session. So here is a brief review of the non-parametric way. So the key message is that we want to leverage the representation powers of neural networks. And actually later we can show that this neural network base or non-parametric base is a universal approximators. But it kind of requires us to solve a computational challenging problems, which is a bilevel programming with neural network-based constraints. So we tried. It is indeed data intense and computation intense. So given this current data availabilities, next we want to see, can we do better? Can we come up with a more computationally tractable one by slightly sacrificing the goodness of it? So this is what we call a semi-parametric approach. So the key message here is we want to parameterize our potential functions as a linear combinations of convex spaces. Here's an example. So suppose we are assuming the deterministic user equilibriums and follows a BPR function. Then we can include two convex spaces. That is, the first is a linear one, and the second is a polynomial one. And our learnable parameters are just the linear coefficient before them. or if you feels like if the modelers believes that the travelers can choose a recursive logic when making their travel choices, we can add one additional entropy basis. Or it is even possible to design other convex spaces depending on the modeler's beliefs or depending on the modeler's domain knowledge. They can have flexibilities to choose how many convex spaces they have and what are the functional forms of it. And these parameters, they will be learned to figure out which component is more important and should be included through the data. So this is so here we're still accepting the primal perspective. That is, we want to enforcing the equilibrium conditions as the constraints while tries to minimize the fitting errors in the objective functions. So here, even though I tried my best, these fitting errors may not necessarily be zero. So I do allows the observations to be not at an equilibrium state, but I'm trying to learn an equilibrium state to better approximate it. So the trick we do here is we replace the equilibrium, we use a value function based equilibrium gap function. So here's how it looks like. Suppose we have a convex potential function, which changes with the vectors of link flow. And we know what, suppose we are attaining the minimum values of the potential functions as the equilibrium point. Now, given any feasible flows, suppose I try to minimize the gap between the potential functions and the value functions. Then actually I'm pushing my predicted flows closer to my equilibrium flows. And that is the value function. That's what this value function with equilibrium gaps tries to do. So the good things of using these linear combinations of convex spaces and the value function based equilibrium gap is twofold. The first fold is under additional technical assumptions. We can indeedly show that these estimators, they can asymptotically yield the minimum possible fitting errors, and under even stronger additions, there are some conditions it can converge to the true parameters of theta. And the second benefit is actually computational-like. So this inverse problems is not a general non-convex optimizations, but instead, we can show that it is actually a special type of non-convex problems. It's what we call multi-convex. You can think of them as if we fix one block of the variables, then these functions will become convex in other blocks. And next slide, we want to show how can these multi-convexities allows a efficient decomposition algorithms. So here's how the decomposition algorithms looks like. Suppose we are having two blocks of variables. The first is parameter, and the second is link flow. So we can iterate, so starting with feasible flows, we can fix flows and only treating the variables as, treating the parameters as variables, and then solving a convex subproblems that only involving theta as the decision variables. And after solving this first subproblems, we can fix parameters as a constant, and then solve the second problems that only involves link flows as decision variables. So the good thing is that, remember, we have many different samples. This second subproblems can be further decomposed by samples, and actually they can be solved in parallelization. And we can show a local convergency with additional technical treatment. So this is what we call the inverse learning with multi-convex optimizations. And I do want to show an empirical case studies that validate this framework. So in this numerical experiment, we are collaborating with general models who offered us a year-long of trajectory data, and also Michigan department using the city of Ann Arbor as a case study. I want to give a brief reviews about experiment settings. So we are using the trajectory data of the evening peak hours for 1 hour for the whole years. And the Ann Arbor networks is it's a slightly smaller than the Chicago sketch network, and we're considering 10,000 audio pairs, which covers 65% of the main demand. So when we look at the empirical data, there are like two context features catch our attention. The first is snow. You know that Michigan is cold. Actually, it just snowed this Monday. So when we look at the data, we can see that people tend to travel less on snow days. And similarly, we can see that people tend to travel less on weekend. So looking at these two empirical examples, we kind of tries to consider two context features. The first is whether it snows or not, or whether it is a weekday or not, when we build our network equilibrium model. So we are calibrating two things. The first is a link performance functions. You can consider that we are trying to calibrate a correction factors of the capacities. That is, we want to correct the capacities depending on whether it is a highways or whether it rains, whether it snows or not. And one findings we have is we are using the basic ratio, the flow capacity ratios raised to the power of 2 rather than the power of 4 as stated in the standard BPRs. Our explanation, we found this empirically works better. Our explanation is maybe the another network is not that congested. So using a quadratic functions can fairly approximate the link performance functions good enough. And the second functions we try to calibrate is we adding a dummy link for each origin and destinations to offer travelers the options of not traveling. And the cost for not traveling will depend on the features of different OD pairs. So here's our result. So yes.
Sorry, so if I understand correctly, so you observe the trajectory data
Mhm.
for a subset of the population,
Yes.
but in terms of flows themselves, what do you assume the flows are?
So here we are using the link travel times to do the calculation because we noticed that it's just a sample of population, so we don't have an accurate estimation of the link flow. So we're using the link travel times in the objective function. That's a good question. Okay, so the benchmark here is we are using the current planning models used by the planning agencies. So we call it the benchmark scenarios. So they only predicted a yearly average travel patterns starting from the 4-step models. So when we try to compare their predicted result with our daily observations, we can show that they have a mean absolute percentage errors in recurrent link time as like 80%. So when we try to calibrate the inverse learning framework, we include context features. And also we do plays with what kind of basis should we include it. We played with a polynomials or quadratic or with or without entropy path. So as we see that since we included the context information, we can reduce the link travel time prediction errors. The best we can get is 35%. So, and additional observations here, if you look at the CPU times, most of the computations can be completed within 2 minutes. So it means that it is very efficient to do the recalibrations or do the updates, so that it means that we can frequently update our network equilibrium models and does not have to, and the time can be really completed in a reasonably fast time. So, and also we look at what's the parameters that the inverse learning framework eventually discovered. And we found that actually it can be interpretable to some extent. So for example, here, look at the OD features. It learns that the parameters, it learns that there's a significant possibility one of the numbers of vehicles at the destination. So it can interpret it as if there are more vehicles in the destination traffic analysis zones, then it is more likely the demand will be higher. And also, it also figured out how these two context features impact the travel patterns. It figures out that people tend to travel more on non-snow days and non-weekdays. Okay.
Excuse me.
Yes.
Are these features very part of your training process, or you just because I thought you say that you only consider non-snow and weekday as a context for the learning process?
What's the question?
I'm asking whether all of these OD features were part of the training process.
Yes, it was included in the inverse demand functions
Oh.
as a feature, as an input. Okay, so quickly summarize what are the two types of inverse learning framework we just discussed. The first is the non-parametric one, which is very flexible, but can be computationally challenging. And the second is the semi-parametric, which sacrifices a little on the goodness of it, but can be decomposed as sequences of convex optimization that is more computationally tractable. So here we do want to highlight that the two examples we discussed are just two application cases. And depending on your own choices and on your own setups of that three choices, there are actually a range or spectrum of different inverse learning frameworks that you can build upon. So this is a very good flexibility, but it naturally raises to the questions. So which one should I choose? Given so many options, which one should I choose? How should I choose to parameterize my potential function? So in the next part, we will look at these questions and give some like theoretical rule of thumb about how can researchers choose between different parameterization approach. Any questions before I go to the next part? Okay. So due to the time limit here, I want to only highlight the high-level intuitions and does not cover this like the tedious technical details. So the key message, we did a learning feasibility analysis of the inverse learning framework, and here's our conclusions. That is, the prediction errors of a inverse learning frameworks can be decomposed into three meaningful parts. The first part is what we call it expressivity errors. It can also be understood as a model misspecification errors. This first source of errors comes because modelers does not have a complete or perfect knowledge of people's travel behaviors. So an example to understand is, say, if the ground truth potential function is quadratic, but you are trying to do your optimizations within linear functions, then the best you can do, there will still be off between the actual observed flows. So the good things of the non-parametric approach is it can be, if suppose we are using a deep enough or wide enough neural network, actually this non-parametric inverse learning framework can decompose this expressivity or model misspecification errors to arbitrarily small as 0. And the second source of errors actually coming from the limited data we have. So in reality, we only have limited number of samples of data, and we are trying to train an inverse learning framework that can generalize well. So we're doing some analysis, and our conclusion is, under some additional technical assumptions, both parametric, semiparametric, and non-parametric approach can generalize. But non-parametric approach, it requires more data to generalize effectively compared to the other two factors. And the third types of errors actually coming from the optimizations of solving the optimization challenges where we try to solve all that inverse learning problems or that bi-level optimizations. And it can be reduces by finding a better solution algorithm. So here are the quick summaries of the third part. That is, we do say there is a trade-off. Say, when we decide how do we want to parameterize our potential functions, if we increase the number of parameters, yes, we can reduce the expressivity errors or the model misspecification errors. But at the same time, it will make the generalization more challenging. Suppose we want to include more data samples. Yes, we can reduce the generalization errors, but that will make our optimization more challenging. So here comes our like rule of thumb recommendations for modelers. That is, you should modelers need to decide their parameterizations based on their modeling purpose and based on what data or what computational resources they have. So for example, choosing the non-parametric approach can be a good option. Suppose you have sufficient data and sufficient computational resources. So there's indeed a trade-off. How many minutes do I have left?
7.
Okay. So the last part, so far we have discussed how to build the inverse learning framework, and then I want to discuss how can we use it to support better decision makings. So in this setting, suppose we already calibrated the inverse learning framework, and we have a well-calibrated potential function here. So for example, here we can consider that as a decision makers, I want to set a best congestion pricing strategies to minimize the social cost, which is measured by the total system travel times or emissions depending on the modeler's perspective. So by using a context-dependent user equilibrium here, we can better capture the uncertainties in travel demand, but there still remains a question. That is, the best we can do is we calibrate the models using the current data, but considering the lifetime of a construction process, we are planning for the future, decades ahead. There will inevitably be some changes in people's travel behaviors, and the models we get here can never be perfect. the errors can come from maybe not all contexts can be properly identified or used as input, or because our parameters there might be some calibration errors and our calibration models is not perfect. Or it can be that the potential functional form we select is still far from what should be calibrated. So now our questions comes, how can we still manage to make a good decisions while using a imperfect models? So to answer these questions, we are using a tool called distributional robust optimization. So here's a quick intuitive illustration. Suppose that there are some ground truth populations in the future, but my current prediction is off. So when I try to do the decision makings, I construct an ambiguity set that includes all different possible perturbed distribution from the input. And then I try to design against the worst possible uncertainties within this ambiguity set. And actually, we show that under some additional technical assumptions, this distributional robust way is more sample efficient in reducing the underestimate in social costs when there are like distributional change from what we expected to be true and what we have in the calibration model. So I wanna show with a small numerical example, and we are currently working on a large scale example. So here we assume that the ground truth context it follows a uniform distribution, but we are making an imperfect prediction. We assume the predicted context actually follows a normal distribution and with shifted means and variance. So we are comparing our distributional robust optimizations with the deterministic optimizations, stochastic optimizations, and robust optimization, which are all like the benchmark models in decision makings on the uncertainties. And here we can see that whether we are having an accurate underestimate or overestimate, the distributional robust always has the best performance in the face of the distributional shift. So that leads us to the conclusion part. So in this part, in this presentations, we're looking at inverse learning with multi-day observation. There are two good things about the multi-day observation. The first is it allows us to learn a non-parametric approach. It allows us to use neural networks to approximate the potential functions. But these potential functions comes at a cost. That is, we need some rule of thumbs, given the flexibilities in choosing the parametrization approach. We need to do some feasibility analysis to understand the trade-off when we select different parametrization approach. And the second good thing of multi-convexity, the multi-day observations is that now we can include these context informations to learn a context-dependent user equilibriums that can predict different equilibriums given different contexts. And that also comes at a cost. So since now for each different context, or different samples, we have a set of equilibriums. If you look at the bi-level optimizations, we end up with the numbers of constraints and the numbers of variables we have will linearly increases with the numbers of samples we have. So in order to handle this like a multi-sample equilibrium constraints more efficiently, we are using differential programming and auto differentiations to enable a scalable parallel computation. And also we try to look at how can we use this inverse learning framework to better support a robust decision making. So here come like some final takeaways. The first is in this framework, we're still following the behaviors assumptions of equilibrium concepts because we believe equilibriums remains a meaningful regularization, even though we have all these machine learning techniques possible, because we are still having a relatively limited numbers of samples. So using the equilibriums as regularizations can help us to do better generalizations or out of distribution generalizations with underlying row network topology changes. And the second command is this inverse learning framework is data heavy. So here, one thing we can do is we can better use the multi-resolution information available in the trajectory data. But at the same time, we need to be aware of that there are partitional bias. So we are looking at this general model data set. We believe that all of them tend to be collected from the high-end vehicles, which are more expensive. So we should be aware of these biases when we try to use cross-source the data to build equilibrium models, to build any models, and then to support decision makings. So the second commands through our discussion is we are now embracing like the modeling and computational innovations to transform a traditional paradigms. And the last thing is, if you remember one sentence from today's presentation, I think it should be this one. That is, I believe that the model building is not the goal. We are building the models not only to predict the models, but want to build it to support strategic decision making. So with this in mind, I believe looking at the prediction accuracy alone is not enough. So we need to build models that are robust and policy sensitive so that the model can be built to really support decision making. And what I showed is just like one minor step, a humble step tries to explore this direction. And I believe that there are more explorations possible along this direction. So there are some like references talking about this different part. We have a survey paper that should be out this or next month. And these two papers talk about how to do the nonparametric and semiparametrics. And there are like two additional ones talking about how to choose from different parameterization approach and how to make good decisions with the imperfect models in the setting of network design. And these are like the other references I mentioned during today's presentation. And thank you very much. I'm happy to take any questions.
So there's one question from the Zoom audience.
Yes.
And then just read the question. I can read the question for you. So the question is, when you say equilibrium, do you consider the traffic flow to be stable at all times, meaning like you inverse the inferior parameters, which you cosine stationary or constant?
So the question is whether, yes, we are all these like discussions we have today, we are considering a static user equilibrium. So one of our current research are looking into the dynamic versions of this equilibrium. And that turns out to be very interesting and challenging, and we are still working on the dynamic versions of user equilibrium.
Look forward to that.
Yes.
I guess there is another type of dynamics, right? So say I make a change to the system.
You mean the day-to-day dynamic?
Exactly.
It's
right?
how the
So-
system evolves.
Exactly.
Yeah, I believe one of my lab mates is working on a related problems and tries to, because if you look at the trajectory data, it offers a continuous observation that captures both within day dynamics, that is, the data is actually collected by 3 seconds, but we try to aggregate them to make sure that the noise is more tractable. So it offers a very fine-grained observations of the within day dynamics. And also because we don't need to deploy the sensors, so we can observe the systems as long as the cross-source data is there. So if you look at them by day, there are like intraday dynamics. So it is possible to learn the dynamics from the both sides, depending. So here we are considering static because we're looking at the long-term strategic decision makings. But depending on what kind of policy questions you want to answer, you can try to capture the day-to-day dynamics or the dynamic user equilibriums, depending on your modeling purpose.
So I'm going back to this question. So you basically saying that there's a weather event, the equilibrium changes.
Yeah.
But that, I mean, that underlying assumption that if there's snow, they will change their paths. Okay, but that's not possible. No, people, I mean, we know that it's not that quick. You know, the change. So you take care of it a little bit on the OD part. So you're changing the demand, but the path choice doesn't evolve that fast. So actually, you shouldn't be seeing that if your data is good, you shouldn't show the big change in the path choice. I mean, I don't know if you looked at that. You know, the demand might change. People might decide not to travel, but the equilibrium on the path choice might not be that sensitive to that weather event.
Yeah, that's a very good point. And actually, when we do the empirical calibrations, we only calibrate the link performance function and the demand function and leave the route choice preferences or the utility functions untouched.
But that might not be consistent with what you see in terms of path choices. Those path choices probably really will remain unchanged for given weather event, snow, whatever.
Yeah, I think.
And the travel times will change, and actually, you don't even have to do it like the way you do it, like make it quadratic from to the fourth, because what will happen is if you adjust the capacity,
Yes.
then the headways will be higher during snow, for example.
Yes.
And that will reduce your capacity, obviously. So you can fit that function. You will see the exact fit. It's not that difficult.
Yeah, that's very good. Like, oh, did I stop sharing? That's very good intuition. So actually, initially when we do the empirical calibrations, we start with the power of 4. And what we do is we try to, as you said, as you suggested, we want to calibrate a context-dependent correction term. So if you look at this term, the maximum speed is a continuous way to describe is a highway or not. And then we consider whether it is a highway or not as a feature, and also whether it snows or not as another feature. And then we also consider a mixture term. So you can think of these terms actually tries to correct the capacities. So yeah.
Well, you're observing it, so you know, I mean, that's fine. But it's not that difficult because you know that when it snows, the headway will become larger and then capacity will be lower.
Oh, are you suggesting that we don't need to
You don't
include it?
Obviously, you don't
I
need
got
to
your
use
point.
the capacity during the regular good weather. It doesn't work that. But the other thing, I mean, if you take the assumption that the pad equilibrium will not change, actually, you don't want to minimize the difference between predicted and observed. Actually, you want to probably maximum because you don't want your model to force an unrealistic equilibrium. I'm just giving an idea. So because in this case, you're forcing an equilibrium which might not exist in reality. It just doesn't exist. I mean, it's unless, for example, they are using the Google services that tell them don't use this path.
Yeah. So if
Because you're forcing the equilibrium. No? You're saying that my observed flows, path flows are in equilibrium, so I want my predicted also to follow that process, right?
yeah, so I do wanna make to echo your questions, I do wanna make a clarification. So that is for all these like 2 examples we presented, we all follow this first, what we call the primary perspective, because we believe that the equilibrium conditions is a good premise to support what if analysis. So we are strictly enforcing it. But I do agree that if you believe that the data is very accurate, yeah, by the way, another reason we should that because we believe the data can be noisy. It has a lot of missing values. We may not observe some OD pairs and we may not observe some link flows. So that is, we try to prioritize equilibrium consistency over the fitting errors. But I do agree that if there are alternative ways to do all this inverse learning. If the models believe that the data is accurate enough, and they do want to highlight fittings, they can strictly forcing it. For example, maybe 0 is too much, maybe something very small, but also at the same time using equilibrium as a regularization.
And then you're running your static assignment for an hourly flow, hourly run.
Yes, the peak hour.
So what do you do if, especially in those like adverse conditions, if you cannot complete the trip in 1 hour?
Yeah,
What
so
happens to those trips?
yeah, that's very possible. We think 1 hour is a reasonable time scales because so here's an hour network is not that long. So it's very likely that the trip entering it will leave it within 1 hour. So it's that's a good suggestion.
Might be losing some trips that cannot be completed in 1 hour.
Yeah,
There might be a problem.
yeah, that's might be a problem, but I think driving from here to here, it in most 20 minutes. It's not a large network as large as Chicago's, but I do agree that if it's Chicago's, maybe we should extend the time windows to make sure that the trip-based settings make a sense here.
And my suggestion is
Yes.
there are some path-based formulations different than Beckman's formulation, and those path-based formulations might give you different results.
Oh, we actually played with that. So we have like it's not on these numerical examples because the path set can be not. The observation is sparse, so we do not observe paths for all the OD pairs. But in our synthetic data set, we do try to experiment with the path-based formulations. And indeed, I was kind of simplify the presentations using only link-based as a representation, but I think all these things can be adapted if we are following a path-based formulation, and we indeed have a good way to generate the path set itself. Yeah, thank you. Like any other questions? Yes, it's
And just a very quick one, it's more on the application side or on implications, because you mentioned about the non-parametric and parametric
Yes.
approaches to the inverse learning. and you said, okay, the data, like whether the quantity of samples would be large or a little bit relatively scarce. But do you have any nuance when we're doing like the Michigan study? If you have only a subset of the sample that's available, it actually have a more stabilized like parameters for the parametric like function. For example, like you have just tell me a number, like 1 million samples, but now you only have 10,000. Whether that and to what point, like have any nuance, like to what point that sample actually provides you a relatively stable result of the inverse? Do you have any
Yeah,
nuance?
so if I understand correctly, the question is there any like the critical number of samples?
Like some nuance. I don't know whether there's any
Yeah.
like hard like threshold, but do you have
That's a
any-
good question. The challenge is we're having 1 year of data. It sounds a lot, but we are using every day as a samples. So we have 365 samples, which is not thousands, even in this case. So that is, so we try to maximize our utilities of these limited numbers of samples. So we're actually including all of them when choosing our data. That is actually the limited number of samples we have, even for a yearly data, is actually the main motivations to move us from this neural network-based approach, looking into a like semi-parametric approach that requires smaller data and smaller parameters, smaller data, and more computational tractables. But if one day we have accumulated the data for 10 years, maybe there will be an answer to numerically answer the questions that just raised.
So how do you convert that limited count data into link count?
We are using the link travel times because we are aware that the
You're not using.
yeah, we believe we try some ways to correct it, but it's just too biased because in our network you have like 2 sensors that collecting the ground truth point, which we believe is inaccurate for us to correctly estimate the count. But there are like 2 ways we think is possible. The first is if for example the PAMs, if they have the sensors, we can readily include the count in the objective function. And alternatively, if you think at the trajectory, because you are collected at seconds, actually they only collected the acceleration and deceleration. I read the literature. There are some papers that using the acceleration, deceleration, the weighting profile. If we have the signal timings, then we can use all this information from the traffic flows to underestimate the penetration. Once we have the penetration rate, we can scalably, efficiently estimate the link travel time, the link flows. But the challenging thing is we don't have the signal timing plans for the Ann Arbor networks. So that is why we didn't include it in the objective functions here. But I do believe that even if using trajectory data alone, it is possible to estimate the link count or link flows at some signalized intersections. I believe that is doable.
So I'm just wondering for the data set that you adopt is from the GM, right?
Mhm.
So what's the penetration rate?
Oh,
In
our
that?
rough estimation is something between 7 to 10%.
Okay. So in general, the more the better, the higher penetration
Yes.
rate, the better.
Yes.
But if it's too high, there's no need for you to make calibration. That's what you mentioned. Right?
You mean the calibration in terms of,
In terms of everything.
you mean even if there are, if I observe everything,
Yeah, everything.
but I cannot observe, but if I want to say I want to change, well, for what if analysis,
Responsive action of the travel. That's what you mean.
if we observe a system long enough, for example, the topology changed gradually, it might be possible to train some like get rid of the equilibrium concept. But even if we are having, for example, increase the penetration rate to 100, but we're still observing the network for 1 year, not that many topology changes happens within 1 year.
Yeah.
So I think there still needs to be some calibrations in order to answer what if analysis questions.
Okay.
Thank you.
Thank you very much, Dr.
Thank you very much, Mike.